Hey guys, Miss Thomas here. We are going to take a brief look at some of the things we've covered this term in Algebra 2B. This will serve as your asynchronous session for Unit 6 and hopefully will also help you better prepare for the final exam by identifying areas that you might need to review before taking the test. To be clear, what I'm going to do today is not to reteach the concepts that you've seen throughout the term. Instead, I'm just going to do a brief review, kind of reminding you of topics that we've gone over as we've gone along. And hopefully this will cue for you whether, yes, I completely remember this concept, everything sounds familiar, I feel confident about it, or, wow, I forgot we did that concept, the things that Ms. Thomas mentioned didn't sound familiar, I know I need to review that. Okay? So again, the goal here is going to be to review. If you do feel like the concepts that you see need to be explained in more detail, you can refer to the course, you can refer to my other help videos or other asynchronous sessions where my goal was to explain in more detail. Again, purposes here will be to go over things pretty broadly and briefly. Starting with Unit 1. So in Unit 1, one of the big things that you needed to know how to do was identify function families, both graphically and just by looking at the function itself. So remember, a linear function looks like a line, okay? And this would be something of the variety of f of x equals x, or f of x equals 2x, or f of x equals 3x, or f of x equals 2x plus 7. These would all be linear functions. And then we moved forward. We also talked about, I don't think we did absolute value functions, so I'm just going to cross that out. We certainly covered quadratic functions, which as you know are representing as a parabola. These are of the form y equals x squared or y equals 5x squared or something like that. The parent function for this would be f of x equals x squared. So what I mean by parent function, every type of quadratic function that you see will be sort of a derivative of that original parent function, y equals f of x. So it should look something like this parabola. Okay. A radical function. This is the graph of a radical function, or a square root function. Okay, y equals the square root of x. Notice that it's all happening in the first quadrant. We're not having any negative values for x or y here. You should also be able to identify a cubic function, which has a little bit of a zigzag in it, cubic meaning x to the third. I don't think we need to worry too much about cube root functions. We definitely went over exponential functions, which as you know, if I've got an exponential function growing, it grows very rapidly at first and then much, much faster over time. So notice from about here to here, the function is increasing, but increasing very slowly, whereas from about this value to here, notice the very rapid growth. So exponential functions, especially one that's growing, grows more and more rapidly over time. Or an exponential function that's decaying or decreasing would decrease slowly and then decrease faster and faster and faster over time. A logarithmic function. This would be of the variety, f of x equals log base 10 of 7 or something like that. You can see we've got this asymptote on the y-axis, and then we've got this growth. Notice that this looks a bit like our square root function. These two parent functions look a bit alike. The difference is, though, you can see that the radical function originates at the origin, 0, 0, and then grows, whereas when we have our logarithmic function, we've got this asymptote that goes on and downward forever. We've got a vertical asymptote. Now, it wouldn't always be on the y-axis. This is just the parent function, which is why you're seeing that on the y-axis. We also took a look at rational functions. And the reason I'm writing over these is just because I suspect they're kind of hard to see on your end. So I've got this rational function. Notice this one, this parent function, which is equal to y equals 1 over x, has asymptotes at the x-axis and a vertical asymptote on the y-axis. So irrational functions are usually pretty easy to identify because they've got that sort of mirror image effect going on. If I folded this paper horizontally, notice that I would kind of end up with a mirror image sort of looking thing with my function. This is another type of rational function which I don't think we dealt with so much. I'm going to cross that one out as well. So again, you should be able to look at these function families, the graphs, and know immediately I see a straight line. It must be linear. One that's not on this list that I should mention is a trigonometric function, which were the ones that kind of had this wavy effect and were periodic. This would be something like f of x equals sine x, or f of x equals cosine x, etc. Quadratic being a parabola, etc., etc. You should be somewhat familiar with end behavior as well, and you should know that how to identify if I have a function written out. So if I had written out, f of x equals 5 to the x, you should immediately know, oh, I see x in the exponent, that means it's an exponential function, etc. All right. Also from Unit 1, scaling graphs and knowing how to identify a well-constructed graph. This concept, I think, is easy in a way but difficult because there aren't any very specific rules about it, but there are a couple things that'll help you scale graphs correctly. So one, if you're given some multiple choice question where it asks you which graph is appropriate, look for one that's clear and legible. If there are a bunch of numbers crammed really close together, if any part of it is difficult to read, it's probably not scaled correctly. A correct graph should also include all of your data, so make sure that if you've got data about x, going from 0 to 20, 0 to 20 should be on that graph, and a little bit more. Okay, so you want your graph to include all of your data plus a little cushion. So for example, if you were measuring temperature on your y value and temperatures ranged, you had values ranging from 0 to 20 degrees, I would recommend that on your graph you showed maybe like -5 degrees to 25 degrees. You know what I mean? Just give a little bit of a cushion, so including the range and the domain of all of your data and then a little bit more. Generally, x will be your x-axis, will have all your independent data, your independent variable. Y will be your dependent variable. Also from Unit 1, substitution. I'm not going to go over this example. It would take quite a few minutes to solve it. And again, I'm trying to be conscious of time here because I know you guys are busily preparing for the end of class. So my tip on substitution: look for an opportunity to easily isolate a variable. So for me, the first thing I see is that this c is by itself. So what I would do, if it were me and I was asked to solve for substitution, I would solve for c. In this example, it looks like c would be equal to 3a plus 4b minus 3. Then I would take 3a plus 4b minus 3, and I would plug it in wherever I saw c in the other two equations. This is how substitution works. You find equivalent values, so instead of c, I can write 3a plus 4b minus 3 in the remaining two. So I would make that substitution, simplify, and hopefully from there I'd be able to get to a solution. Now another option I could have done, you can see that a down here is by itself. I could have taken this and solved for a and done substitution with a. That would have been fine too. But again, look for opportunities where it's going to be easy to isolate a particular variable. Now going into Unit 2, a big theme of Unit 2 was isolating variables. This is something you guys have been practicing in your first semesters of algebra. The most important thing to remember is your order of operations, PEMDAS. If you can keep that straight as you go, isolating variables should be a breeze. And of course, write out steps. I recommend that you do every step one by one. Sometimes I'll see students try to combine and take care of a couple things at once as they're isolating variables, and what ends up happening is that you forget to equalize things on both sides. You make silly mistakes. So write out each step one by one. Be careful, double check your work, and above all, remember your order of operations when isolating variables. Another thing we learned in Unit 2, finding inverses. This is kind of an extension of isolating variables because really you are still just going to be solving for a value. If you are given some function and asked to find the inverse, so for example this f of x, there are two key things you need to do. First, you're going to switch your x's and y's around. So if we say f of x is equal to y, which I think we're all familiar with, the first major step is taking y and replacing it with x, taking x and replacing it with y. Once I get to this step where I've flip-flopped all my x's and y's around, I'm going to solve. I'm going to solve for y. So notice here I've got y on this step isolated, and I now replace it with f negative 1 of x, which is the notation for a function's inverse. Okay, so key step is switching x and y and then solving for y or solving for the inverse. Okay, other than that, making that switch, this is no different than trying to isolate any other variable. Logarithms also came up in Unit 2. Be comfortable with switching back and forth between exponential and logarithmic form. This is exponential form, 3 to the 10 equals x. If you were asked to write it in logarithmic form, remember that logarithms are exponents, okay? Logarithms are exponents. So in logarithmic form, I would have log base something of something equals an exponent, because logarithms are exponents. So my exponent here is 10, right? So I'm going to have some logarithm that is equal to 10 because 10 is my exponent. My base, let's see, it's base 3. And then x goes here. X is my result, I'll call it. So this is equivalent. 3 to the 10 equals x, written in logarithmic form would be log base 3 of x equals 10. For the most part, students have no trouble determining that this 3 here becomes the 3 here because it's log base 3, the base of the exponent. Usually students just confuse that remaining part with 10 being the exponent. I see it put here a lot. Remember that logarithms are equal to exponents. Remember that exponent should be by itself on the other side of the equal sign. And I think that'll help you place that remaining value because there will be nowhere else to put it. Okay, so switching back and forth between logarithmic and exponential form. One other thing to remember, the natural logarithm is in base, that's a typo, base e. The natural logarithm, the difference between natural log and logarithm, this has a base e. Logarithm has a base 10. It's the same thing to write natural log e of x, okay? These two statements are equivalent. We don't have to write that base e because it's assumed. That's what natural logarithm means. Same thing if I just write log of x and I don't specify the base, it's assumed that I'm using base 10. Okay? We know that we could be using other bases. For example, here it was log base 3. If you're using some other base besides 10, you have to specify it. So again, if I have ln of x, ln x, or natural log x, we assume that the base is e. If I've got a log x, we assume that the base is 10, and that's the difference between these two. That also explains why the natural logarithm and e are inverses. Let's continue. A couple logarithmic laws you should know. Again, I just wanted to throw this up here so you were aware of kind of the list and the expectations on this. I'm not going to go into examples, but you should know the laws regarding addition, subtraction, products, and quotient rules regarding logarithms. In Unit 3, you're introduced to transformations, specifically translations, reflections, and dilations. Remember, a translation is something that moves the graph left, right, up, or down. Okay? So that would be something like if I had f of x looking like this, I could transform it and move it downward. This would be a translation. On the other hand, I could have a reflection across y or a reflection across x. If I reflected across the x-axis, my green function would then look like this, right? It's a mirror image. If I reflected across the y-axis, it would just look like itself, right? Because a parabola is already a mirror image of itself. And then dilations are shrinking or stretching, compressing or stretching. So I could dilate this two ways. Again, looking at my original green function, I could horizontally compress it and make it skinnier like this. This would be a horizontal compression. Or I could stretch it out doing something like this. And I'll show you more about the notation of these things on the next slide. But understanding your definitions of translation, reflection, and dilation are important, and how they would look on a graph. So again, translation, moving the graph up, down, left, or right. Reflection, creating a mirror image across some line of symmetry. And then dilation is the only one that actually changes the shape or the size of the graph. Again, dilation is the only one that changes the shape or size. Reflections and translations are just kind of, you could take it and you could pick up the shape, whatever it was, and just move it somewhere else. Again, dilation actually manipulates shape or size. So, what does that look like when we're notating? Mapping statements are important. So when I was talking about vertical translation, moving something up and down, well, up and down is happening on the y-axis, so it's something that we apply to f of x as a whole. So the mapping statement would be f of x maps to f of x minus plus or minus k, where k is just some constant value. Again, notice that I've got k being added to f of x, kind of telling me that it's happening to y. If it happens to x, like here we can see in the horizontal translation, we've got something happening inside the parentheses with x. This is a clue that it's something happening horizontally or on the x-axis. Okay, so again, if it's happening at f of x, it's happening vertically. If it's happening to x, it's happening horizontally. So same thing when we start to look at vertical dilations. If I take my f of x and multiply by a on the outside, this is something that I'm doing to f of x, to the function as a whole, so it is vertical. And then again, applying something inside with x, you can see is a horizontal dilation. Reflections are the only thing where things seem a bit backwards, but let me explain. So reflection, I've got a reflection on the x-axis. Notice that the mapping statement has the negative sign on the outside happening to y. The reason that we have that negative sign on the outside happening to y is this. Imagine that I'm reflecting a parabola across the x-axis. If I reflect across x, what changed in my parabola? Did I change the x values or did I change the y values? I changed the y values. If I compared, for example, if I looked at this point and then its correlating point in the reflection, this point right here, if I look at these 2 points, maybe the value of this is 3, 2, those would be the coordinates of that point, and then my point on the red parabola, this would be 3, negative 2, right? Every point on the parabola has the same, if I slice it, has the same x value that it had before. The only thing that happened is that I took all the y values and I multiplied them by -1. I made them all negative, okay? So again, hopefully you can see that there has been no left or right shifting, no x shifting in this graph. The only thing that's happened is that all the y values have been swapped. Swapping all the y values moved it across the x-axis. So reflecting across x, we're only changing y values, which is why this negative is being applied to f of x or to y instead of x. And it's the same thing when you reflect across the y-axis. The negative symbol is applied to x, because when I reflect across y, what I'm actually doing is taking all the x coordinates of the function and multiplying them by -1. Okay? These are just more mapping statements, horizontal translation, vertical translation, horizontal and vertical dilation, and again with the reflection in y and x. They are explaining the transformations that are happening in the inverse. This is a really handy table. You can find it, you can take a screenshot of it here, but you can also find it in lesson 30 in the review for unit 3. Okay, let's press forward. In Unit 4, we start to talk about probability. Remember that the probability of an event can be found by taking the number of outcomes in the event or the number of ways that this thing can happen. For example, if we're talking about the odds of drawing a king out of a deck of cards, well, there are 4 ways I could do that because there are 4 different kings, right? So that'd be my numerator, and then you divide by the total number of outcomes, or in my example, that'd be the total number of cards in a deck, which is, what, 52, right? So the probability of event, the total number of outcomes that that event could happen, or the number of ways it could happen, divided by the total number of outcomes that could happen, period. We also want to be aware of complementary events. Complementary is almost like an opposite event. It's either that event is happening, A is happening, or A is not happening. When I add complementary events together, when I add their probabilities, I always get 1. So for example, the probability that today is Tuesday plus the probability that today is not Tuesday. Well, there is a 100% chance that either today is Tuesday or not Tuesday, right? So if I add the probability of today being Tuesday, 1 in 7, plus the probability, because there's 7 days of the week, right? Plus the probability that today is not Tuesday, because there's 6 other days in the week. If I add 1/7 and 6/7 together, I get 7/7, which represents a 100% chance of something happening, right? Now, complementary events are not always written in the sense of happening or not. For example, I could have said the probability that let's say I am going into, I don't know, let's say that I am on a path and it has a fork and I either have to go left or right. There could be, I would add together my probability of turning left and my probability of turning right, and those would equal 1, because those are the only 2 options I have. And so my point of that example is that it's not just always the probability of something happening and something not happening. It's just the point is that I know that 2 events are complementary if when I add their probabilities together, I get 100%. Okay. We also need to be aware of dependent and independent events. Independent events are events that are not connected. The probability of them happening is not connected. For example, if I draw a card out of a deck and I get the ace of spades, then I put it back in the deck, shuffle, and draw again, the probability of drawing any card was not affected by my draw, right? Because I put the card back. So the probability of drawing an ace of spades again is still 1 out of 52. Dependent events kind of snowball on each other. For example, if I have a bag of marbles and 3 out of my 10 marbles are green. Let's say I draw a green marble out of the bag and I don't put it back, I keep it. Well, next time it's going to be harder for someone to draw a green marble, right? Because I've taken one out. I've affected the probability by not putting that marble back, because now there are only 9 marbles in the bag and only 2 of them are green. So beginning with a probability of 3 marbles out of 10, I took one of the green marbles out. Now there are only 2 green marbles out of a total of 9. That's dependent. Usually it's easier to spot dependent and independent. The difficulty is usually calculating dependent. Remember, like in the example of replacement, which I just used, where I didn't put the marble back, I didn't replace it. Remember that the denominator is affected as well. So I didn't just say, now my odds are 2 out of 10. I said, now my odds are 2 out of 9, because the total number of marbles, that denominator, was affected as well. Statistics. Okay, so guys, Just so you know, this is the last unit where I'm going to kind of just briefly talk over a couple topics. I've decided not to include Unit 6 because you guys will have just gone through Unit 6 and it should still be pretty fresh in your head. So Unit 5, we got into statistics. Remember that a population is the collection of all the individuals that the study is talking about. A sample is just some portion or percentage of the population. A parameter is some figure, some characteristic that was determined from information about the population. A statistic is something that was determined from a sample. So for example, if there are 30 people in my class and I poll all 30 and they all say that green is their favorite color, I've determined this parameter for my population. If I only ask 5 out of the 30 kids and they all say that their favorite color is blue, I've determined a statistic. Okay, response variable versus explanatory. It's kind of like dependent versus independent variable. That's a good way to think about it. An explanatory explains why a response variable is happening. For example, I noticed that 5 of my students have tutors and those 5 students have really high grades. So the explanatory variable is that they have a tutor and the response is their grades. Now there could also be lurking variables and bias. I think we know what bias is. It's something that's making an experiment unfair. A lurking variable is a variable that I didn't take into account, that I should have controlled, but I didn't. For example, maybe I am looking at if we're still talking about grades. Maybe I've got my classroom set up into 5 study groups. And I want to see how each student performs within their own study groups. But maybe I've put myself, the teacher, in one of these study groups, and I don't account for that. Well, it makes sense that the study group with the teacher in it has some bias, right? They're probably going to get a little bit more information and clarity than these other groups. So I've created this lurking variable that I didn't account for. Lurking variables are something where conditions are not even or not matched when they should have been, and it affects the outcome of the experiment. Margin of error and confidence. Remember that margin of error is found by just taking half of a confidence interval. So if we say, for example, that we estimate that 60 or to 70% of people will pass this class, if I want to know the margin of error here, I take half of that interval. So 60 to 70, that's an interval of 10%. Half of 10 is 5. So the margin of error is 5%. Now they'll also give you resources such as the reference sheet for z-scores and sample sizes. Anytime that you're offered some sort of resource to click on, I absolutely recommend that you use it. Those resources are there to make your life easier, okay? For example, with those z-scores and sample sizes, it'll be something where you can look at, they might tell you the population size and how many people will be sampled, and from that, just using their reference sheet, you'll be able to figure out what the z-score is. You'll be able to figure out the confidence interval or confidence level, rather, the margin of error, right? So given most of those criteria, you'll be able to figure out the missing thing that they want you to find. Okay, so I know this has been kind of a fast and furious review. Again, as you see, it was very broad. So if at any point there was a question where you thought to yourself, I wish you would have given us a complete example and solved it, go back and find an example and solve it. In lesson 30, there are unit reviews for every unit of the class. And you can kind of do a brief thing or a long thing. And here's what I mean. If you open up, for example, the Unit 1 review, there will be a practice section, which essentially takes you back to the Lesson 1 research section in full. Or there will be like a check your comprehension thing that'll be much shorter. It'll just ask you 1 or 2 questions to kind of test your knowledge and give you some basic review. So I would recommend looking at the comprehension check for each of them and then maybe picking out, the 3 or 4 hardest things for you in the class, and then actually going to the practice sections, which will be much lengthier. Now, my general advice on the final exam: 1, keep your vocabulary handy. Even if you know what a word means, I recommend just looking up the definition of it anyway, especially if we're talking about anything having to do with statistics and probability. Very minor parts of a definition might affect what your answer is. Of course, double check your work on the final exam, and again, use your given resources. And if you have time, take a second attempt on the final exam. The exam will be cloned if you ask for a second attempt, which means you'll only have to go back and fix answers you got wrong. The catch is that you can't ask me for a second attempt until you've already completed your first one. That's just the way the gradebook is set up. So you have to ask me before the end of my office hours on Friday at 11 a.m. If you ask me later in the day, if you ask me over the weekend, I'm not going to see it, and you're not going to be given a second attempt, okay? So if you want a second attempt on that final exam, make sure you ask me. And remember that your final exam is worth 15% of your final grade. So it is absolutely worth your time to study for it, to review for it, and to take the second attempt if you do have time. Okay, guys, again, I hope this has given you a general overview of some of the concepts you can expect to see on the final. Go to lesson 30, use all of the reviews. There will be no new info given to you. It'll all be reviews, so use that resource to help you prepare, and I wish you the best of luck. Thanks, guys.